Thank you for joining. We're just going to give people another minute or two to join the meeting here. We still have a few people trickling in here. We're going to give it a few more seconds here. Okay, let's get started. So welcome to our webinar, Optimizing Precision Motion Control for Automated Imaging. I'm John Garrity, Strategic Marketing Manager here at Dover Motion, and I'll be moderating this webinar. I've got an electrical engineering background and 20 years of experience in precision motion control. Sitting here in the room with me, we've got from Dover Motion, David Dig Thomas, who's a Principal Systems Engineer. He's in his 9th year as a member of the engineering team. He's the architect of our embedded smart stage ecosystem products and a precision motion stage design expert. Dig is always looking for the latest chips and design approaches and tools to increase motion stage resolution, performance, reducing noise, and reducing power consumption wherever possible. We're also joined here with Prab Gaurasankaran. Prab's the Vice President of Engineering and Strategy at Performance Motion Devices, also known as PMD, and he's responsible for future-proofing PMD and their customers who innovate in a fast-paced technology environment. He's got a degree in electrical engineering and an MBA in finance and strategy from Babson. Prab brings over 20 years of technology and product management, hardware development, and engineering leadership to the PMD team. As we begin this webinar, feel free to enter any questions into the chat. We'll be collecting those, and then at the end of the event, we'll be answering those questions. So keep those coming into the chat as we go. And with that, let's get started. So this is just our high-level agenda. Some of the topics we'll be covering, and as I mentioned, we'll be going through questions at the very end. So we've already done the introduction, so I'll skip that and jump right in here. Thank you, Dig.
Sure. So yeah, starting off, we've been integrating PMD's ICs in our products for, I'd say, about 6-7 years now. Our first product was the DOF5 D-Stage Focuser. I remember the first time Chuck Lewin came over, founder of PMD, he saw the stage. So you can see in the top right-hand corner, what he saw is the fully buttoned-up version. And we looked at it and said, wow, that's nice. It looks like any other stage that you make. Good job. And we said, yeah, but the controls are inside. Okay, great. Where's the box? Like, no, they're inside of the stage. And finally, he looked in there, realized we were telling the truth. And from that day forward, it's been a great partnership. We've been formed DOF5, Smart Stage, and other products in the family. And what's really enabled to do that is, or enabled us to do that, is the high quality and performance that PMD, specifically the MC58113, offers. 20 kilohertz position and current loop, which 10 years ago that was pretty much reserved for semi external control, do a quadrature, correction, specifically an autofocus, and follow the surface. That will definitely help your throughput if you want to keep moving and move your Z-axis at the same time during the scan, or if you're doing field imaging, want to make sure that your Z is where it should be by the time X and Y get there. Um, additionally, field-oriented control is on there. That's sort of standard these days. PID, feed forwards, bipod filters in the forward loop. Another really nice thing is the ability to do open loop moves. This may not seem obvious, but oftentimes, especially when attempting to do computation, find yourself up against a hard stop, down against something, if it's Z-axis, how the balance isn't set correctly, or basically just somehow stuck in normal computation, be it as robust as it may be, will not work. So we have the ability to do open loop moves, which basically allow you to drive in one direction or another, such that you can get out of that spot and commutate, or move to a known position, such as a limit switch or home flag, and simply load your commutation phaser from that point. And excellent.
Yeah, thanks, John and Dig. Yeah, just to add to what Dig had mentioned, so the basis for Dover's architecture is the MC58113 chip. It's a 100-pin TQFP, so that has all the motion control capability that Dig had talked about in the previous slide. And a few of them that he had highlighted, the first one was obviously FOC, the field-oriented control. Obviously, it's pretty standard now, but as you can see in the block diagram on the right, there's a lot of compute that has to happen, right? So you have the Clark Park transforms, the inverse Park transform. And so just implementing this FOC algorithm native inside the chip is a big benefit for Dover and Dig. So it got them a building block that already has things that they were looking for. The other capabilities that are already there inside the 58113 that Dig had covered was the PID loops. So obviously there's a profile generator where you can do a bunch of different profiles, S-curve and trapezoid. And there's a PID after that, and then that gets forwarded on to a current loop. So having both the PID that is tunable, so you can set the KPKIs, and having a current loop native to the chip benefits Dover a lot. So that way they don't have a lot of discrete parts, because as Dig showed in the last slide, it's a pretty tight squeeze to get all the controls inside the stage. And they have all the mechanical super accurate motion, right? So just having a chip that can do all of it helps them a lot to get to that level of integration. On to the next slide.
Actually,
Yeah, real quick,
Go
actually.
ahead, Dick.
Dig, you want to touch on the current loop a little bit?
Sure. I just wanted to add to the advantage of having that current loop versus just standard PID. I know many people out there just use the PID position loop, but effectively what that current loop does is it decouples your PID position loop, which is based on your mechanical plant, and the electrical plant, which is based on your resistance and inductance of the motor, such that effectively all your PID loop needs to know about are the sort of physical moving things and what is the force constant of your motor. Beyond that, when you tune that current loop, you can pretty much take your position loop and move from motor to motor, as long as you know whatever that force constant is, and you're not sitting there having to decouple and sit there and tune and turn one value up. I like to think of it as, for those who remember the old TVs where you actually had to turn the knob, or the radios, imagine if you just had one knob and that was to adjust the volume and change the channel. That would be kind of painful. This is like having two separate knobs, one for volume and one to change the channel. So it's extremely valuable and makes tuning much, much simpler.
Yeah, and I think the other part that Dover uses a lot is the biquad filter. So we put two biquads in there. So it gives them a lot of flexibility to kind of tune the mechanical system, right? And take out harmonics and uncertainty in the system. So all that is is built into the chip, and then we kind of customize some of the capabilities based on algorithms Dover had provided to us. Yeah, we can go to the next slide.
Sure. So this is a simple encoder resolution versus speed table. Again, one of the advantages of having everything integrated inside the drive and in close proximity is you have great signal noise ratio, and you are not sending digital quadrature or very sensitive analog over several meters of cable. So we are actually able to, on our latest platforms, go down to resolution of sub-nanometer, basically, almost roughly 300 picometers, and still maintain a reasonable peak velocity. And once you get up to about 1.5 nanometers and above, we can achieve 1 meter per second. So, really being able to have the best of both worlds, this high velocity capability as well as super fine resolution for the high precision, all due to this integration.
Right, and I think typically what we see is, 1 to 2 count in position stability with a lot of the products. So very stable due to that kind of low noise design.
Great.
Yeah, and in terms of the capabilities inside the chip, right? I think these are a few that Dover and DIG use, but there are a lot of commutation options that we provide. So they had actually worked with the algorithmic phase in it and algorithmic commutation option. So there's a few that, like the pulse phase in it, where there's 3 short pulses. If you look at the integration that I put in on that linear stage, you can't move the motor a lot for getting the initial phase. So we are able to do it with very, very small motion. And that way initialize the phase angles correctly. And that benefits them a lot because obviously there's not a lot of room there in terms of linear motion that we can do. The other part of it, Dig, if you want to talk about the direct set stuff that you guys use.
Sure. It's similar to a method you all already implement where once passing the index mark, it automatically loads the phaser for the commutation. But in this particular case, we allow the customer to pick a particular switch, be it a limit switch, home switch, if they do not want to use the index, and then they can perform a move even by hand, depending, if you're just setting it up for the first time, and it will automatically load the good known phaser into that position, and at that point your commutation is set.
Yeah, and where we see a lot of application benefit is if there's an interference based on the sequence of axes coming up in an instrument, and you're looking to move safely. We've got a half travel vane, so if you want to move directly towards the center of travel of the stage to avoid any collisions at the extremes, you're able to do that without having to worry about the stage waking up and shaking during normal kind of algorithmic commutation. So it allows you to move to a safe location, set up your commutation, and you can start moving from there for your homing routine.
Yeah, and then we obviously have built into the chip with some of the essentials, right? Like the temperature monitoring. So we have support for external thermistors, so you can put them in different spots based on your characterization. That helps you for safe shutdown and to prevent overheating, especially with the level of integration they have and with everything sealed. So these are super critical for the implementation of that stage. We also monitor the bus voltage. So we do an under and over voltage. And it's an analog input that's used for bus voltage monitoring. So that kind of lets you set the thresholds, especially if, say, you're running at 24 volts, you can set your over voltage limits and gives you a level of protection for safety. The key one, especially tied to the motor, is to protecting the motor is the I squared T, where it's current over time and it's an integral of it. It's almost like the energy, and you're trying to prevent the motor from overheating and preventing short circuits. So that's very common and it's a very useful safety limit. So Dig, if you want to add to how you guys use it in your application?
Sure. Typically, we set that here at the factory based on which model stage and which type of motor is in there. And it's really a function of what is that peak current and the continuous current, and what levels of accumulated energy, as you put it, we're comfortable with. We test that here and then basically bake that into the standard product. So here as well, one of the great options for the trajectory on the MC58113 is to be able to switch between trapezoidal moves, where it's sort of a square wave for acceleration, and then a more natural and realistic S-curve, where acceleration actually ramps up and jerk is more of the impulse. So in this case, you have trapezoidal shown on the left, you have S-curve shown on the right. And if you look at the table in the middle, it basically gives you, a little bit of information about each one. And at first glance, it's kind of like, what's so great about S-curve? Well, yes, it uses more power, it takes more time, but one of the key things here is it produces much, much less energy in the harmonics. Why does that matter? So in a perfect world, you would have a sinusoid for all of your cell velocity, whatever, and you wouldn't excite anything outside of that single frequency. But when you have a triangular motion, like I said, it's a square wave for that acceleration. So imagine just bam. That's for your acceleration, and it's bam for your deceleration. So whatever isolation you may be on, whatever system, those harmonics, those odd harmonics, all the way out, are going to excite different modes in your system, on your stage, in your mechanics, whatever. Whereas F greatly attenuates those. Again, at the cost of some time and some power. But in the end, that often ends up with a overall shorter move and settle time. Because with triangular, you may make it in 80% of the time, but then you spend another however long sitting there trying to settle because you've excited everything in the room. S helps solve that.
You also kind of get a smoother move, right, through your S-curve because of the smoothing of your acceleration.
Exactly.
Yeah, and the other capability that this is all built into the chip is the feed forwards. Dover uses it for both the acceleration and velocity. So if you look at the block diagram on the right, it kind of shows a view of so there's the PID loop, and then you have the feed forward compensation. So you have the acceleration feed forward on the top and the velocity feed forward on the bottom. And that kind of takes out, so if you look on the left, typically acceleration feed forward kind of compensates for inertia or mass. And so you want to have a much cleaner, smoother motion. So it gets rid of that. And then the other part of it, the velocity feed forward, kind of gets rid of the drag, I would say. So those two together really help. I'm sure Dig will show graphs and stuff in terms of how he's compensated for these and made much smoother motion. And these are things that you can tune in your lab, right? When they built the stage, they calculated these based on the mechanics, and we're able to smooth it out and make much cleaner motion. The other part of it that they use, jerk, which is just when you look at it later, as Dig showed in the previous, it's used in the S-curve profile. It's like a second derivative of acceleration, and that helps you set so it gives you a little bit more tunability in terms of setting your acceleration.
Thanks, Prem.
Right. So continuing on the feed forwards, to me, these are kind of like freebies that nobody takes advantage of, or not everyone. So you have acceleration feed forward and velocity feed forward available to you. And as Prab mentioned, the acceleration feed forward is really like a mass proxy, and the velocity feed forward is proportional to drag. Think viscous friction. If you're going fast enough, the air friction. But more realistically, what you will see in a stage is the proportional loss due to eddy currents. As you go faster and faster, you get that drag from the eddy currents themselves. So if you know what those values are, typically most people know what their payload is, you can, for all intents and purposes, cancel that out in terms of what the PID loop would see. So imagine you can go in and do your theoretical calculations of, here's how much force I need to move my mass, and here's how much viscous friction or drag I need to compensate for. And once you have those correct numbers, those components go to zero. So now your PID loop comes in and has much, much less work to do. It can really focus on disturbance rejection, which is what it's meant to do. And trying to keep that position error as small as possible. And you're not worried about, cranking your integral up because you're just trying to get the thing to pull into position. So let the velocity and acceleration feed forward do as much of the work for you as you can, and save the, variable work for the PID. So how do you do that? Do you do it correctly? Well, here at Dover, we developed a proprietary tool which will actually identify and optimize both the acceleration and velocity feed forward by estimating your mass, as well as by estimating the overall average drag in your system. And so, if you don't believe me, look at the graphs below. So here on the left, it's a little colorful, so I'll walk you through it. The reddish plot is the actual position error, and the purple, nice, pretty, smooth, well-behaved plot is the commanded trajectory. So where the arrow is pointing is basically where the trajectory said, hey, you should be finished. Clearly, we were not finished. We still had roughly 2.5 microns of error. And that was using a well-tuned PID. So if you come to the right-hand side, you have a well-tuned PID with well-tuned feed forwards. Again, red is your position error, purple is the commanded trajectory, and basically they line up. It's almost theoretical. It ends where it's supposed to. And in this case, you have, significantly less error, 10 nanometers, you're in window. So in terms of increasing throughput, reducing vibrations in your system, this has huge advantage.
Yeah, and this profile also uses the S-curve or jerk that we discussed earlier. So again, trying not to excite resonances within the system or the structure, and then in addition, adding the feed forwards, you're able to see very good, stability right when the trajectory is complete.
Yeah, it's actually very interesting to dig to see. We build these standard algorithms. It's always fun to see how you use them. It's amazing that you get to 10 nanometer error with
Yeah. It's a 5 nanometer stage,
books.
so it's
Yeah,
just
you read them in the books and say, oh, this is how you should use them. But
yeah.
it's amazing to see.
Now that's what, even the current loop and the current control that you all offer. I remember talking with Kevin a few years ago, and when he saw the plots of the current stability and at 2 milliamps or 3 milliamps, it just blew his mind. Usually there's that dead zone, but with the MC58113, you're really able to have a very high dynamic range of current control. And again, that's huge for us.
Yep. Yeah, and I think Dig, you can talk to this. You kind of use this feature, right? The sinusoidal profile.
Yes, so certainly Bodhi plots are a wonderful tool for anybody trying to tune anything, electrical engineers, mechanical engineers. Stages obviously fall into this category. So PMD actually has built-in sine generator, which is great. You can just put in the frequency and it takes care of the rest. You don't have to worry about going through and creating tables and whatnot. So for frequency sweeps and identification, this is extremely helpful. Additionally, for any customers out there who would want to see how their plant behaves once they put their payloads and whatnot on there, this is invaluable. So this is an example of one of our tools utilizing the sinusoidal profile generator, where we generate typical Bodhi plot with both closed and open loop data. And it's the amplitude on top and phase on the bottom. And I guess I should point out that, this is our Smart Stage 150 and yeah, the 3 dB. Well, there's 3 dB and minus 90 degrees. As nice as the 3 dB makes things look, we feel that 90 degrees is kind of a better metric, more robust. So if you look down at the bottom, that puts us at around 257 hertz bandwidth. So not too shabby.
Yeah, this is another feature. I think Dover uses them. A lot of other customers use it. It's used in like mobile robotics. And so if you look in the bottom chart, it kind of shows applications that use this UDP feature. So we talked about trapezoid and S-curve profiles. This gives you a user-defined profile mode where it's a table. It's actually two tables, and you kind of loading a set of points. And it's almost like path planning, where the controller will follow that set of points. You give it a PVT kind of settings. And so it's used a lot in scare arms, and if you have a repetitive pattern, or even in mobile robots where if you don't have a lot of time to send commands and you want to send a lot of updates for position points, you're able to load a table of these points and traverse a path through. And the picture on the right kind of shows how it's applied, and how the contouring, or in this case, the UDP profile is applied to our position loop. Dig, how do you guys use that, or?
Yes, so we're going to talk about a couple of uses. So there's obviously the coordinated motion with multiple axes, and our Smart Stage XY supports that. Either one axis can be the primary and the other the secondary, or vice versa, and they can handshake. And basically, one will follow the encoder output of the other and along through a UDP table. And so we have customers who, or potentially following a scanning axis with a focusing axis, again, to help improve throughput. That way, the z-axis is already there and settled at the same time the scan axis gets there, or the sample. So another example, somewhat simpler, is the single axis version. So basically, the UDP is looking for some sort of time input, or a tick or a pulse that can be generated internally, but it can be externally as well. So from the internal point of view, you can basically put whatever arbitrary table you want and generate that type of move on a single axis. So here is just a simple sine wave, but some customers may want to generate some sort of frequency sweep or something with certain frequency components, or a canonical move that they do with their equipment. And it's easy for them to give us that table and say, hey, go test this, or for them to test it themselves.
Yeah, we actually have a question in the chat from the UDP mode, so I'll read that. So in UDP mode, is it possible to ramp up the frequency gently?
So in short, yes. You basically can, you set the time axis, which is on the left, and then your position, which is your second column in your 2D array. And again, it can be an arbitrary function. So if you, however you want to generate that chirp or whatever, that can all be done through UDP and a user-generated table.
Great, thanks.
So these are customized features which PMD has basically implemented into our firmware. Working with PMD is great. We truly see them as a partner, and we're able to have these great features like position accuracy compensation, which we're always looking for, 3-letter acronyms. So it's what it sounds like, accuracy compensation. Fairly standard. Basically have a 1D table, you put in a value, and you set a dimension. So whether you're compensating on a rolling millimeter, centimeter, whatever, pretty straightforward there. Trigger on position, this is an extremely powerful feature. I've seen this it's on other controllers, but we really did a lot of work in setting this one up to make sure that it covered all the bases. Because a lot of controllers, well, it works with this encoder, but not with this encoder or with this resolution. So we have the ability to do incremental trigger on position. You can basically set your trigger spacing in number of counts. Each count represents the resolution of your encoder. And you say, here's a start position and end position. And you can see that in the graph. Basically, there is your velocity in green. The blue is what we call the trigger gate that is also exposed. So let's say you want to take a series of images while at the same time gating a light or a laser or something like that. And then turning it off at the end such that you don't overexpose whatever your sample is. Or if you're using laser for ablation, safety shutter, again, same principle. We have other examples and abilities for trigger on position, but save those for another day. Lastly, repetitive motion enhancement. This is an extremely powerful algorithm and capability that we have. So if you look on the right, you can see at the top where it's a series of steps and settles. And what you're seeing that looks like somebody took a sledgehammer and hit the table, that's the positioning. And we have a tool which basically goes through and analyzes those moves on the structure and generates basically cancellation profile. So think of your noise canceling headphones or something like that. And that way, the next time you run those moves, it knows what to expect, and it is able to cancel out that ringing and the disturbances that you do not want. So if you look at the bottom graph, you can see the position error is much, much, much smaller and greatly attenuated. And as you might imagine, this leads to significantly improved settling time. So your movement settles, in some cases, are dropped by an order of magnitude.
Yeah, one thing to add on the custom features. So we actually value this a lot because we work as a motion control partner and kind of because you guys are experts in your areas, so you have super unique algorithms. So Dig has shown a few here. There's a few others like bump detection in robotics. There's a bunch of other custom features that they require, and they have an innate knowledge of how they want to implement it. So we kind of put it in firmware on the chip, and then we then sell that as a custom chip to, so Dover buys a custom version with all this customization in there. And it helps you get that real-time customization, right? Without having to do something on the host to implement this. It makes it simpler. So we work hand in hand. We jokingly say Dig has an office at PMD. But yeah, I've worked with Dig a lot. So it's very beneficial both ways.
Absolutely.
So in addition to the kind of chip level view of the world, we've also got some tools basically to help optimize your precision motion application. So for tuning and optimizing your moves, and even doing programming of an instrument. So the Motion Synergy API software, what you can see here is a user interface for setup. You can name moves, name trajectories, save those to a configuration file. And then in addition, we've recently added some kind of basic tuning wizard functionality where you have like a bandwidth slider that you can use to increase the response of the system, and then do some quick plots and see how that affects your move and settle time. And we've got the times called out, as well as some graphical representation of how long are these moves taking, so that you can more quickly optimize your parameters for quick move and settle. Once you've kind of done that optimization, that same API includes code examples in multiple languages: Python, C Sharp, C++. And so those console examples are already compilable, and you can run multi-axis systems basically much quicker. So it's increasing your development speed for both optimization and then for programming within the instrument.
And just kind of coming back to the chip that they actually use, the 58113. So it does support, so the block diagram on the right kind of gives you a high level view of all the interfaces it supports. Obviously, you see the bus voltage and the temperature, all the safety stuff we talked about. One of the benefits is it does do multi-motor. So a single chip can be interfaced to either a brushless stepper motor or a brushed motor. And it's basically settings inside the chip in NVRAM, and you can program to have to support any of those motors. So it's actually for large OEMs, they tend to want to just use one chip, one SKU, and work it across lots of axes. I know you guys use it that way too, right? Dig in a couple of cases, you've used them for brushless and stepper.
You don't want to deal with 10 different part numbers.
Yeah. So this is actually a very common request where we've actually seen like they have a design that goes in the stage. We have some end OEMs that have done a one-axis design, which just has this chip and then the amplifier design based on the machine they're doing, and they would use it all across the machine. They would have 90% of the software written, and then they could plug and play these cards in lots of places. So this is another capability that we have that you guys use. Yeah, and just to highlight, so obviously Dover does the super high precision nanometers precise motion, right? So there's other things within your instrument. So this is kind of showing an example of a robotic arm. Actually, we've seen it in some of the lab automation applications. They would use a Dover stage for microscopy, but they would have a robotic arm, let's say, taking samples and moving it or positioning stuff. And this is showing a rendering based on our newer N series drive product. It's a 3-card stack. It has the 58113 on the middle card, and then it has a 1 kilowatt amplifier. And this is kind of showing you can put one per axis distributed across a robot arm. So the benefit for both of us is they may have picked Dover first for a stage, and then they see that they're using PMD inside and the C motion is exposed. They tend to want to use PMD in other axes. And these N series drives use the exact same software. So 90% of the software is the same. It just has the built-in amplifier. Some of the lab automation guys don't want to touch the amplifier side. They don't want to do the analog part of it. So this kind of has an integrated amplifier. And this is showing a gantry example for liquid handling, pipetting, lots of different use cases. And it's showing a three anion, it's one per axis controlling the XYZ there. So just to give a view of how else do people use PMD, and you can go from the chip that Dover is using. Typically, if it's lower volumes, they would do the drive product, and then if it's higher volume, they'll go down to the chip. And in Dover's case, they needed the level of integration. If you look at their stage, it's super integrated, so there's not a lot of room for a drive, but there are other applications where it makes sense.
Great. Yeah. So earlier, I think, in case you missed the very beginning, we're basically discussing how we've taken the chips and gotten everything within the structure of the stage as far as the feedback, the drive circuit, and then the control chips. In addition, we do, where it makes sense for precision applications, we've got our external DMCM controller, and that's multi-motor as Rob described. So that can handle either stepper or linear servo motor, brushless motors, so three-phase motors or stepper motors. We're also showing some custom capabilities where it makes sense. We're always willing to engage on those custom designs. So there's a very compact 3-axis linear motor servo system on the right. And so that's a full camera optics module with XY motion of the sample as well as a Z focusing axis for the objective. And that's in a 10-inch height package there that we work with a customer to kind of scope that out. And then in addition, we can do the on-axis kind of moving controls boards, but we've also got multi-axis kind of application specific where it makes sense assemblies. And we're showing an example of a 3-axis servo board there as well on the left. So we're kind of wrapping things up here. So what I wanted to do was leave a few minutes for some questions. So if you have any of those, please type those into the Q&A section of the webinar. And we do have a couple queued up actually. So I'll start going through those. So I guess for both of you, what's available for precision motion control now that wasn't available 5 or 10 years ago?
Yeah, I think for us on the PMD side, we're starting to see more and more advanced encoders, right? Obviously, like sine, cosine, I think you guys use them. We're starting to see BIS absolute encoders. So there's more innovation in the encoder side of things. And obviously, electronics have become cheaper. So that's driving down cost and made them a lot smaller to implement. And we're starting to get newer algorithms that are very application specific. So instead of trying to put it in our standard chip, we starting to create a library of custom algorithms that we could implement based on end applications.
Great.
Sure. So just to follow up on Prop's point, absolutely. Many ultra high precision, high accuracy feedback devices, they just keep improving and improving. It's insane how precise they are now. But even so, more on the mechanical side, just the reduction of tolerances, much tighter control. We're just waiting for the magnets to keep getting stronger at the same pace.
Another one here. What is the best way to coordinate my hardware autofocus with the stage motion?
So typically what we recommend here at Dover is through, if your autofocus device offers step and direction or quadrature output, since these are both digital signals, you don't have to worry about any signal corruption, to feed those into the electronic gearing mode on the either DOF5 or Smart Stage Z.
Great. And we're at time here, so I'm going to end with one more question that came in. So can I set up outputs to indicate when an axis is in motion or settled?
So yes, you can. There are a few ways of doing that. The most common way is through a breakpoint. You basically choose the output you want and set the breakpoint to trigger once you have settled, and you will see a 5-volt signal go high, and that's how you do it.
All right, we do have time for one more here. So I think Prab, this one's more for you. So does PMD offer stepper controllers? If so, do those stepper controllers offer error correction mode instead of the problematic full servo with a stepper and lead screw?
Yeah, so PMD does offer a stepper like we talked about, like the 58113. It treats it as a two-phase brushless, essentially, right? So it can actually do closed loop stepper. And to your question, where you can actually customize the algorithm. So we can work with you to say, if you don't want certain parts of the closed loop done, but certain other parts done, we can work with you on having an intermediate. Like you talked about a unique use case, I guess. And we can support it.
Great. Well, I hope that was informative for everybody. If you have any questions, feel free to follow up with us. And thank you to Prab from PMD and then Dig from Dover Motion.
Thanks a lot. This was a lot of fun.
Thank you very much.